All right, so I'm gonna pick up where we left off in probably, I think, the second of 4 videos. This will be the 4th, I think, I'm counting right. But we left off knowing that F1 and F2 were both upward. The sum of their forces was 392 newtons. That was our first equation. And we then had to consider the torques because we had to consider something else because we couldn't solve 2 unknowns with 1 equation. So we've already kind of gone through placing the hinge at the center, which, would help, but it's going to make your lives harder than they need to be. And the previous solution involved placing the fulcrum at the first leg, which, since it's on the end, seems like the easier thing to do, seems like probably the better thing to do. But if you decided to approach this in a different way, maybe a little bit of a harder way, if you put your fulcrum at leg 2, it'll work just the same. And hey, if you're really thorough, you could always do both to check your work, make sure you get your answers right. So again, I'm going to start by considering the number line. And in this case, that's really going to be a helpful step. So if we consider I'm calling it a number line, I guess it's not officially a number line. If this is our 0, and this is our 6, I'm not even gonna put M's on them for meters, I'm just gonna put the numbers, so whatever. We know that along here, we have our table center in the middle. This occurs at 3 meters. We have mass B, which occurs 1 meter from the end, or at 5. Darn it, I wasn't going to put meters. So object B exists at 5. Our leg 2 exists at 4. F2 to avoid a little numerical confusion. Object A exists right here at 1.5. So that's our number line. And that's kind of where you need to start. I'm going to copy this so we can use it. All right, Control G, C. All right, so now the only difference between the way that we solved the last one and the way that we solved this one is our placement of the fulcrum, which will make a fancy triangle this time. So our fulcrum now is being placed.
Have your attention in the building. Status of our water main break. There's a small, shallow hole out back with a lot of water in it presently. Still no determination on status as to when it will be repaired. So the water is still on at this point. Staff, if you wish to leave, you may. Those who wish to remain, by all means, you're welcome to. We will be here till 11 p.m. tonight. Teachers, please make sure that your IPRs are in prior to leaving the building.
Hey, they are. All right, so our fulcrum is here.
They're in prior to leaving the building. There's still 2 pages of teachers that need to include the person I'm looking at right now. Thank you. Let's have a night.
So recall that the L here is the distance between where the force is applied and our fulcrum, or the axis of rotation, or the hinge, or whatever the heck you want to call it. So these L's are going to be a lot different than they were the way that we saw the previous problem. So this L is going to change a lot. And let's kind of go through those before we start doing some calculations. I should add that our F1 occurs here at the 0. So recall that the L is, well, the distance between where each of these things happens and our fulcrum. So, first of all, the L for object 1 is the distance between this and this. And so that's hopefully fairly clearly 4 meters. The distance for object A is the distance from where the force is applied to where the fulcrum is. So since this fulcrum, since this fulcrum occurs at 4 meters and object A occurs at 1.5 meters, the distance between those, hopefully you can tell some real quick math in your head, the distance between those is 2.5 meters. So object A is going to exert a torque 2.5 meters from our fulcrum. The table, which we'll call LT, occurs at 3, this is 4, so LT is going to be 1 meter because this force is exerted 1 meter from where our fulcrum is. The length for force 2, I do not need to consider, because if our fulcrum's here, force 2 is not going to cause any spinning. Force 2 is just going to cause the whole thing to like move up. It'll only cause it to move up because like it doesn't, there's no distance between where the force is applied and our axis of rotation. So we don't need to consider force 2 in thinking about our torques, just like we don't need to think about force 1 in considering our torques in the first one. We do need to consider the length of object 5 though. I'm sorry, the length for object B. Object B occurs 1 meter from where our force is. So LB is again going to be 1 meter. That part's important. If you're going to get this stuff wrong, this is like a really, really, really common place to mess it up. So the number line is real helpful when you're doing these problems, at least on the hard ones. Easier ones, you probably don't need to worry about it, but hard ones you do. Okay, so anyway, so I'm going to consider, so this is my fulcrum or the hinge. Oh, I don't know, whatever. So that's my fulcrum. Come on, go away. Stop it. Whatever. All right, so that's our hinge, and we have some different forces, and each force is going to exert different torques. First of all, the force due to object B is going to exert a torque like that. On the previous slide, we calculated LB to be 1 meter. Oh, you know what? I'm not going to color the picture like that. Other forces. There is the downward force of the table. There's the downward force of object A. Then there's the upward force supplied by leg number 1. So take a minute to digest. Does that make sense? Here's our fulcrum. With respect to the fulcrum, FB goes that way, the downward force of the table goes that way, A goes that way. So hopefully this picture makes some sense. I think it's helpful. So it'll help us figure out like the directions of the torques. Now, if you're being very thorough about it, which you most certainly are welcome to be, you should consider the idea, and I'm going to do this separately from this, so this is a little bit differently than we typically approach net force problems. The net torque is going to be 0 Newton meters. So that means that the sum of all of our torques is going to add up to be 0. So, thinking about this, you have to consider positives and negatives. And you have to consider the fact that F1 will go that way, the same direction as FB. So the torque that exists due to leg 1 and object B are both in the same direction. They're both clockwise. They both go in the same direction as the clock. So they would have negative torques. Object A and the table itself would cause spinning to occur in the positive or counterclockwise direction. So these torques are positive. The torques existing due to these forces are positive. The torques existing due to these forces would be negative. What the heck was that? So yes, you could be thinking about it in a negative way, and that'll totally work, and that is A-okay if that's how you or your teacher do it. Totally fine, do it up. I would think about it a little bit differently, just like the same thing. It's just easier to me to not have to consider negatives. So to not consider negatives, the torques in the positive direction, which are torque A and torque T, torque existing in mass A, torque existing from the table, are equal to the sum of the torques from leg 1 and object B. So for me, this would be my working equation because I'm allergic to negative signs. So these are your torques. Well, this is going to be our working equation. From here, we're just going to have to go calculate a whole bunch of torques. So let's go ahead and do that. And it's mostly pretty easy. So keeping that in mind, I'll put that like sort of in our back pocket. The torque that exists due to object A is equal to the gravitational force on A times the length of A, or the distance between where it's applied and the axis. So in our case, object A was Well, it's equal to the mass of A times gravity times LA, which was what? Our LA was 2.5 meters. So it's equal to the mass of A, which I think was 9 kilograms, times gravity times 2.5 meters, and you should get 220.5 Newton meters. Next, let's calculate the torque due to the table. So the torque due to the table is equal to the downward force of gravity on the table times the distance between the table and the axis. T, G, LT. This number should have worked out to be 232, oops, 235.2 Newton meters. Finally, the only other torque we can calculate just yet is the torque that exists due to mass B, which is equal to the gravitational force on object B times the distance between object B and the axis, which should end up being 68.6 Newton meters. And again, if you're more comfortable considering positives and negatives, this you would make negative. Okay, so then shoot, we're going to come back to this equation. If we do, we'll see that the torque from object 1 is going to equal the torque from object A plus the torque from the table minus the torque from object B. And when you go ahead and do that math, you should find that the torque for object 1 is 387, oops, 387.1 Newton meters. So that's our torque 1. And from there, things are kind of easy from there, I hope. We'll keep that, head to the next page. So once you know that, you have an equation for it. Well, torque 1 is also equal to force 1 times the distance between where that's applied and our axis, which we had previously found to be 4 meters. So F1 is just going to be torque 1 divided by L1, or that. And through some math, you should find this to be about 96.8 newtons. And once you have that, we're just going to head back to equation number 1, which was that F1 plus F2 is 392 newtons. There we go. So F2 equals 392 newtons minus F1, or, oh, I don't know, what the heck was it again? 295.2. So there you have it. That's your second type of mechanical statics problem. The first type is the hanging stuff hanging with strings. 6th period, we've done that in class together. 4th period, we'll do it in class tomorrow. There's also an extensive solution posted on Edmodo about how you go about solving those problems. It's sort of the same idea. It's the whole idea between, or the biggest idea among all this is really that F net is 0. And hanging statics, all you have to consider is forces, so that's kind of nice. But for tables, you also need to use this to start with. Then you'll have to consider that the net torque is also 0. So that should be that. All right, thanks.